Okay, so the biggest news is your first exam is Wednesday. So exam 1 is this Wednesday. And the topics are everything we've done so far, so up through 1D particle kinematics. So we're just going to spend the whole day today just doing example problems on the most recent stuff. And then after that, we'll get into new material. There is a lab this week. And we're going to start in lab thinking about vectors and two-dimensional motion and stuff, but we haven't done any of that in class yet. Remember that to get ready for the exams, so exams and quizzes are two different things. To get ready for the quizzes, which we postponed last week, you just skim your notes, read your notes, and I'm just asking short answer questions about like what I say in class. But to get ready for the exams, you just want to do repetitions on your assigned problems, okay? The exam questions are going to be very much like the assigned problems that I give you. Well, we haven't done too many yet, so you might be able to just go through all the problems again. Like I think probably doing the problems more than once is a really good idea for anybody. But I always say, generally speaking, I think the best way to prepare for the exam, because remember, they're all cumulative, is go back to the first problem I assigned and just ask yourself, do I know the steps to do this problem? And if you can think like, okay, first I do this, yes, then I do this, then don't spend a ton of time on that problem and just go to the next one. And just wait until you get to problems where you're a little hazy on what to do. And then spend some time trying to work through that, get yourself restarted with the solution if you need to. But if you think about it that way, it's a way that you can kind of look at all the problems, remind yourself about all the problems without actually doing every single one, because obviously that takes more and more time as the class goes on. Yes?
Are you going to give us the 3 formulas on the exam?
Yes. Every formula will always be given on my tests. Yep. Yes?
How many questions is the exam?
I try to make it an hour. So you guys have 80 minutes. I try to make it an hour to give people a little wiggle room, so you don't feel like you're racing against the clock. But that can be a different number of problems depending on, what kind of problems they are. But 4 to 5 is probably usually the most likely. Maybe with a couple of parts each one, that sort of thing. Yes?
For number 9 on the 1D homework, when is that due? Is it due next Wednesday or today?
I think it says it's due tonight. And then, but let's check. What?
The weekly one is next one.
Oh, the weekly one. Okay.
And then, but 9, I think, is.
Okay. So yeah, the one question number 9, I think, is due today. But then the weekly assignment is due like a week from, I don't know.
Wednesday.
A week from Wednesday. Thank you. And if you have any questions about the daily problems, I'd be happy to go through it. Any other questions right now? Okay. Well, let's just keep going through example problems, and I'll try to hit a lot of the types of things that can come up in these sort of problems. So last time we did the video of that big building that they could suck all the air out of, and you could watch 2 things in free fall with different weights, the feather and the bowling ball. And then we started talking about free fall and projectile motion problems. So let's get back to that. Okay, so let's say that an object is launched straight upward. From a starting height of 2 meters. With a starting speed of 8 meters per second. And so let's first figure out how high the object is at its highest point. Then second, we'll figure out how long it takes for the object to hit the ground. And then third, we'll figure out what's the object's velocity just before it hits the ground. So the first thing you have to do with these is just be able to visualize what's going on. Sometimes you need to read a problem a couple times. I think it's a good idea. Like just you with these kind of questions, you want to read it until you could describe what's going on in different configurations, like reword it to somebody. That's how you know you have all the information in your head, you know? So this thing is starting at a height of 2 meters. It's being shot up into the air at 8 meters per second. And we're trying to figure out some stuff about how high it gets, how long it takes to hit the ground, and how, what's the velocity right before it hits the ground. So I'm going to sketch a little picture of what we're talking about. So this distance is 2 meters. And it's starting from here and going up until it gets to a highest point. This is all one-dimensional motion, so I have it drawn as if it's moving just barely horizontally, but remember, all it's really doing is just going straight up and straight down, okay? Everything we're doing is happening just along a line, back and forth along a line. And the first thing we want to figure out is, we want to know this distance. So to start doing that calculation, the first thing we have to do is we have to choose what we're calling the positive direction and what we're calling our zero position. And then we have to choose the two stopwatch instants, okay? I always pretty much choose my zero position and my positive direction the same way on free fall problems. I choose my zero position to be at the lowest point that is talked about in the problem. So that would be the ground in this problem. It's usually the ground, but sometimes something else. And then I just always choose my positive to be up. And it doesn't matter which way the object is going, positive for me is positive is always up and negative is always down. And then the two stopwatch instants, you're going to choose those based on when you're given information and when you're trying to find information? Well, we're given some information about what happens right at the start of the motion. We know the speed and the direction, we know the location, and so it makes sense that our time equals 0 is going to be when the motion starts. That's when we click the stopwatch on. And then anytime you're trying to figure out information at a single instant, then that instant has to be one of your two choices. Otherwise, you can't do the problem. And so our time final is going to be when it reaches the highest point. Okay, so now based on these, we can go through the list of variables. So there's 6 possible variables: time final, acceleration, P initial, P final, V initial, and V final. And I try to just always go through them in that same order, just so I don't forget any. Okay, so first of all, do we know what the stopwatch says when the ball gets to the highest point? No, but we're not asked for that, so I'm not putting that anywhere. Do we know the acceleration? Yeah, we always do in free fall. It's down at 9.81. If you always choose your positive direction up, then it's always going to be negative 9.81. So A is equal to negative 9.81 meters per second squared. And one thing that can be confusing about that is, since you don't really have a way yet to think about what acceleration, to visualize acceleration, people tend to mix up acceleration and velocity. And that makes people start to second guess, like, wait, this ball's on the way up. So do I need to make the acceleration positive at the start and then make it negative at the end? But remember that the velocity is going to be positive at the start and negative at the end. But the acceleration is just what gravity's doing. It's always pulling things towards the ground, whether they're going up or going down. And you can sort of make sense out of that if you think about this. Remember that if something's speeding up, velocity and acceleration are in the same direction. And if it's slowing down, they're in opposite directions. Okay? So when you throw something up into the air, it's slowing down as it goes up, right? Because it's going to eventually slow down and stop at a highest point. Well, that means that if the velocity is up, to slow down, the acceleration has to be down. So even on the way up, acceleration is down. Then on the way down, it's speeding up as it moves towards the ground. The velocity is down. That means the acceleration has to be down there too. So gravity always does the same thing. It causes an acceleration downwards. Yes?
Will we be given the velocity of falling with air resistance on the test?
No, the acceleration? Or
Acceleration, sorry.
yeah, without air resistance, that 9.81, that's the only acceleration we're going to use for free fall, and I'll give you that, yep. Really, there's almost, excuse me, there's almost no like constant or equation that I wouldn't give you if you wanted it. The only possible exception is in unit conversions. I might make you use like a certain set of conversion factors, you know, but basically if there's ever an equation that you'd like that isn't on the test, just come ask me and I'll write it up on the board. Okay? Okay, so acceleration we know. Do we know the position at time equals 0? Okay, we know that, so let me just, like early on, let me just sort of think it all through here. So we're calling the ground 0, okay? And positive is up. So if at time 0, the object is 2 meters above the ground, then that position is going to be, you know, what do you get if you start at 0 and go 2 meters in the positive direction? You'd be at positive 2. So initial position is positive 2 meters. And then, do we know the position at time final? No, that's what we're trying to find. So I'll put that over here. Do we know the velocity at time 0, time initial?
8 meters per second.
Okay, yeah, and let's think about the direction again carefully. So remember that a velocity is a speed, and then with a plus or minus that tells you the direction. Okay, in this case, is the object, so we know that it's going to be plus or minus 8 meters per second, because that's the speed. Is the object at that instant moving up or down? Up. That up is our positive direction, so this is positive. And then, okay, we've been waiting this whole time to use this fact. Remember I said that anytime you have an object in projectile motion reaching its highest point, at that instant the velocity is 0. You can think of that as the definition of reaching the highest point. So any question that asks you about the object's highest point, you know at sometime during the problem you're going to have to use the fact that the velocity is 0. So our V final here is 0. Okay, now we're just looking for an equation that works. And this is the one that'll work. We'll go through and make sure. So first it has to have the variable you're trying to find, and it does, PF. And now all the other ones, A, we know, PI, we know, VF, we know, VI, we know. So this one will work. So 2 times negative 9.81 times the quantity, PF minus 2, is equal to 0 squared minus 8 squared. And so negative 19.62 times the quantity PF minus 2 is equal to negative 64. Now divide both sides by negative 19.62. And you get PF minus 2 is equal to 3.26. Now add 2 to both sides, and you get that P final is equal to 5.26 meters. Okay. So that's the position. It really asked for the height, like how high above the ground. And so you might want to just double check and make sure that the way you've defined position, this is telling you the height. But we defined our 0 position to be at the ground. So this is how far up it is above the ground. And so that's what we're being asked for. Anyone have any questions about that? Okay, next we want to figure out from the instant it's launched, how long does it take for the ball to hit the ground? So if you turn on the stopwatch when it's launched, leave it on as it gets to the highest point, leave it on as it falls, and then click it off right before it hits the ground, what does it say?
Sorry,
Yeah.
Is it possible to have chosen just that position 2 meters up as your initial position?
As your zero position,
Yeah.
yes, you
so
could do that.
Would be okay.
That would be okay, but then here's the thing.
You wouldn't -2.
Yeah, so then at the end, like these questions usually ask stuff to you kind of in English, not in physics. So it's not asking you what's the final position exactly. It's saying how high above the ground is it.
Gotcha. Okay.
So you would have gotten an answer that said 3.26,
Okay.
and the math would have been perfectly right. But then you'd have to think like, okay, I got to also take into account that extra 2 meters,
Okay.
and you'd have to add that on separately.
Okay. Thank you.
Yep. Okay, so the first thing you have to do in parts B, C, D, whatever, is ask yourself, the choices that I made for time equals 0 and time final, and position equals 0 and the positive direction, are those still okay in the new problem? I mean, I guess the positive direction and 0 position, those always you can keep them the same because those are just pretty much arbitrary. The two instants are the ones that sometimes you have to change. And in this case, you do. Our time equals 0 is still the instant that we want to turn the stopwatch on. But now we're asked for something specific about when the object hits the ground. So we can't turn the stopwatch off when the object gets to its highest point. We have to let it continue all the way, okay? And so what that means is any of these initial values, P initial, V initial, those still hold. We can use those values that we knew before. But the stuff that we knew about the final, about time final before, those don't mean anything to us anymore because we're stopping the stopwatch at a different instant. Okay, so our time equals 0 is still going to be the instant that it's launched. But this time our time final is going to be the instant just before it hits the ground. And so based on these, let's go through again and think about what variables we know and what variable we want. Okay, we're trying to find how long it takes. So time final is the thing that we're trying to solve for. Acceleration, we still know is negative 9.81. P initial is still positive 2 meters. Do we know what the position of the object is at time final? 0. Yep, it gets back to the level of the ground and we called that our 0. So P final is 0 meters. V initial is what it was before. That's positive 8 meters per second. And do we know the velocity right before it hits the ground? No, we're going to try to calculate that for part C. Okay, so is there an equation that works with these? I think the one that should work is this. PF is equal to PI plus VITF plus 1/2 A TF squared. So this one has TF. PF we know, PI we know, VI we know, and A we know. So this equation will work. But this is an example of a problem where solving for the time can be a little bit of a pain. So when I fill this out, what we're going to see is that we have a quadratic equation. And the variable that we're trying to solve for is the one that's squared. And so we're going to have to use the quadratic formula for that. So PF is 0, PI is 2, then we have plus 8 TF. 1/2 times A is minus 4.905 TF squared. And think for a second about how do you know when you have to use the quadratic formula? How do you know when there's not an easier way to solve this? So you always have to use the quadratic formula if there is a constant term and a term where your variable is linear, that's the 8TF, and a term where your variable is squared. If all three of those exist, then quadratic formula is the way you have to go unless you're going to try to factor it and stuff. I don't think that's probably usually worth it. Especially with like this crazy decimal, you know, like it's unlikely you're going to come up with that. Okay, so if you're missing any of those three, then there's probably an easier way to do it. If that 2 is gone, so you only have a linear term and a squared term, then you can just factor out a t, and it's really quick. If the linear term is gone, then you can just separate the two pieces and take the square root. So that's easier. But in this case, we're just going to have to use the quadratic formula. Yep.
Will the quadratic formula be on the test?
Yeah, I'll give it to you. Also, if you are interested, come talk to me at lab or after class or something. And it takes me about 1 minute to enter, if you have a TI like graphing calculator, to enter the formula into your calculator, and then you never have to use, you know, you can just punch the values into your calculator and it'll spit out the answers. So let me know if you want that. If you remember, the way you do the quadratic formula is, so the coefficient of the variable squared is what you call A. The coefficient of the linear variable is B. And the constant is C. And it's all based on what those coefficients are. And the formula is, so a quadratic equation always has 2 roots. And the 2 roots are negative b plus or minus the square root of b squared minus 4ac. That's all in the square root like that. And then divide everything by 2a. And so this is negative, so negative b is negative 8 divided by 2 times 4.905. Well, so I'll just put this as, we got negative 8 plus or minus 64 minus 4 times negative 4.905 times 2 all divided by negative 2 times a is negative 9.81. So this is number 9. We first have to start with a unit conversion. It says that this rock is thrown up into the air from a height of 1.5 meters with an initial speed of 35 feet per second. 35 feet per second. We want to get that into meters. per second. 1 meter is 3.281 feet. And so that initial speed is 10.67 meters per second. And we're going to start by calculating how high the rock is at its highest point. This starting height is 1.5 meters. I'm going to choose time equals 0 to be when it's launched. And time final is going to be when it reaches the highest point. Okay, this is a question about the highest point. So when you see that, you're always waiting to write down the one bit of information you always know you're going to use. What's that?
Velocity is 0.
Yes, at the highest point, the velocity is 0. We have to use that. You can't, there's no other way to solve problems like this. So the 0 position, I'm going to put at the ground again. Positive is up, negative is down. And now I'll start going through what I know and what I want. We don't know how long it takes. We know that the acceleration is negative 9.81. The initial position, what's the initial position? So if you start at 0 and go 1.5 in the positive direction, we're at positive 1.5. We're trying to find the final position. The initial velocity, it's moving up, so we know it's going to be positive. And we just figured out that the speed, so the speed is 10.67 meters per second. And since it's going in the positive direction, we'll take the positive. And then the last one in the list is the one we know we have to use. V final is equal to 0. The equation we can use here is 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So that says 2 times negative 9.81 times the quantity pf minus 1.5 is equal to 0 squared minus 10.67 squared. So that says negative 19.62 times the quantity pf minus 1.5 is equal to negative 113.85. Divide both sides by negative 19.62. and you get PF minus 1.5 is equal to 5.80. And so PF is equal to 7.30 meters. So these first three are, the steps you follow are exactly the same as the steps for this example that I did here. Was that the first example I did today? So maybe I'll skip a few of these and go on to some stuff that's asking new questions.
It was mainly the displacement.
Displacement, yeah. Okay, right, displacement. Well, that is part E and F. Okay, so displacement, I haven't mentioned this yet. Displacement is the later position minus the earlier position. And so if it asks you for the displacement between two instants and you know the positions at those two instants, you can always just plug that into this and you're just subtracting them. So in this case, the displacement, the later instant, so it's asking for the displacement from where it's thrown to the highest point. So the later instant is the highest point. The earlier instant is where it's thrown. And so this is just going to be 7.3 minus 1.5, and you get 5.80. And the displacement, because of the subtraction, it can come out negative too. I'll bet the second one, yeah, the second one does it. So it says now for F, what's the displacement from the highest point to the ground? So the displacement is the position at the ground, because that's the later point. That's 0, because that's where we chose our 0 position, minus the position at the highest point, which was 7.30. And so that comes out to be negative 7.30 meters. I think we're actually going to do that in lab today, if I remember right, a couple of things with displacement. I just haven't said that yet. Anything else interesting on this one? Oh, well, let's draw these arrows too. Yes, question.
Sorry, quick question for lab. Is there anything that we're gonna learn in lab that we need for the?
Yeah, that's a good question. No, they're pretty independent.
Okay, cool.
Yeah, lab is pretty much always just its own thing.
Okay.
In this case, this is the closest you would ever get to something like that because I'm happening to mention displacement in lab. But I just don't tend to ask displacement questions on tests very often, and I just have it in a few spots still on homework questions. Okay, so for parts H through K, it's just asking for draw the directions of arrows right after it's released for velocity and acceleration, and then speeding up and slowing down. So let's say we're going to draw the direction of the acceleration the velocity just after it's released. The velocity on the way down. And then it says something a little vague about explain how this works in terms of speeding up and slowing down. Okay, so let's just draw two separate pictures on the way up and on the way down. Basically what we're doing here is drawing pictures as we kind of explain the same thing that I talked about at the start of class. So here's the object, but it's on the way up. Here it is on the way down. On the way up, the velocity, the direction of the velocity is always the direction the thing is moving. So the velocity has to be like that. On the way down, the velocity has to be like that. Gravity is always doing the same thing, whether the object is moving up or moving down. Acceleration is always, for a thing in free fall, downwards. So acceleration is like this, and here acceleration is like this. And now you can make sense out of that by thinking about whether the thing is speeding up or slowing down. When you throw an object up into the air, the whole time it's going up, it's slowing down, getting closer and closer to stopping and coming back down. And so you'd expect velocity and acceleration to be opposite each other. And you can see from this picture they are. So the fact that they're opposite directions is explained by the fact that it's slowing down. Once it gets to the highest point, its whole time coming down, it's speeding up. So you would expect velocity and acceleration to be in the same direction in that case, and you can see that they are. Any questions about that? Okay, so does everything always have a downward acceleration of 9.81? No, remember that only is true for objects that are in projectile motion or free fall, and also when you're neglecting the effect of air resistance, So like right now, my calculator sitting on the desk doesn't have a downward acceleration of 9.81 because the table is keeping it from being in free fall. Okay, that's something that's going to be a little confusing when we start talking about forces and stuff, because gravity is always acting on this. It's always applying a force to it, but it's not always making it accelerate. It's only making it accelerate when other things are not holding it still, All right, well, let's stop there. So test on Wednesday. There will definitely be some questions on this kind of stuff, and then lab this week.